Molecular orbital theory is currently the most commonly used theory of covalent bonding in chemistry. So valence bond theory is very successful. It works quite well for a lot of molecules. But a big failure of valence bond theory is its inability to predict the magnetic properties of molecules. A good example of this is explaining that Y is O2 magnetic, but N2 is not. Now, in order for a molecule to be magnetic, it must have unpaired electrons, and it has to be what we call paramagnetic. And you'll see that valence bond theory can't explain this. So molecular orbital theory is an extension of valence bond theory. And what happens in molecular orbital theory is that we say that electrons are located in what are called molecular orbitals, and these molecular orbitals can extend over the entire molecule. And how you create these molecular orbitals is by combining the atomic orbitals of different atoms. So once the atoms come together, their atomic orbitals don't really exist anymore. We have new molecular orbitals that are combinations of the atomic orbitals that are mixing. So atomic orbitals describe an atom's electrons in terms of waves. And so when the atomic orbitals on two atoms come together, their waves can interact in one of two ways. They can either interact in phase, which gives rise to what we call constructive interference, and the amplitude of the waves in this case will get bigger. The waves basically add, and remember that amplitude of the wave is equivalent to probability of finding that electron in a particular region of space. Or the waves of the two atoms can come together out of phase, in which case we'll have a peak meeting up with a trough, and the waves will cancel out, giving you zero amplitude in the overlap region or no electron density. So what we're really saying is that when the atomic orbitals, the waves that represent those electrons on the individual atoms, come together in phase, and we get constructive interference. In the overlap region, we get increased electron density. But when those electron waves come together out of phase, they cancel out, and we get no electron density in the overlap region. So the wave functions describing overlapping atomic orbitals, they can be combined in one of two ways, either in phase, giving us greater amplitude in the overlapping region, and we call this bonding molecular orbital, or they come together out of phase, and in that case, in the overlap region, you get decreased electron density, and we call that an anti-bonding molecular orbital. So this is two hydrogen atoms coming together, and they're going to be overlapping their 1s orbitals. And if those orbitals come together in phase, then you're going to get increased electron density between the two atoms. Okay? If they come together out of phase, you're actually going to eliminate the possibility of there being electron density between the two atoms. So this is called bonding because it helps hold the atoms together. And this is called anti-bonding because you actually eliminate the possibility of there being any electrons in between the two atoms, because these are the centers of the two atoms here. So that does not help the atoms hold together. In fact, it prevents the atoms from coming together. So an anti-bonding orbital results with a region of zero electron density between the two atoms, whereas a bonding orbital results with a region of increased electron density between the two atoms. So here's a picture showing how we construct what's referred to as the molecular orbital diagram. So here's on the left, we have an isolated hydrogen atom. It's got its one electron in a 1s orbital. And over here, we have a second isolated hydrogen atom. Again, it's got one electron in a 1s orbital. This is the same thing written out but using orbital diagrams. When these two atoms come together to form the molecule, these 1s orbitals are going to overlap. They can overlap in phase, which gives us a bonding molecular orbital, and we have increased electron density between the two atoms. Or they can overlap out of phase, and then we end up with a region with no electron density between the two atoms. We call that a node, but we have a little bit of increased electron density actually away from the center of the atom. These orbitals are labeled according to what is being mixed. When s orbitals are being mixed, we form sigma molecular orbitals. Sigma is just the Greek letter for s, sigma. We label the sigma orbital with the type of atomic orbitals that are being combined to create it. If it's a bonding molecular orbital, we don't put any superscript there. If it's an anti-bonding molecular orbital, we always label anti-bonding molecular orbitals with a star. So we would describe this, generally we would say this is the sigma 1s orbital, and then we would say sigma star 1s or sigma 1s star. So when these guys come together, we had one electron here, one electron here. These are the orbital diagrams for our individual atoms. In the middle here, we had a molecular orbital diagram for our H2 molecule. Now we had one electron from each atom, giving a total of 2 electrons. So we have to put 2 electrons into our molecular orbital diagram. So they're going to go 1, 2, and there they are. They're all paired up. So H2 is what we call diamagnetic. Is that wrong? It doesn't have any unpaired electrons, and we wouldn't expect hydrogen to stick to a magnet. Now, it's kind of fun because we can actually now write electron configurations for molecules, not just for atoms. And so how we generally do that is the orbital gets put in parentheses. So in this case, the orbital containing the electrons is sigma 1s, and then the number of electrons gets written as a subscript outside the parentheses. So that's your number of electrons out there. And then in here, we've got the orbital type. Okay, and some molecules are going to have a long list of orbitals. In molecular orbital theory, we can calculate this concept called a bond order, and bond order is really easy to calculate. The bond order is just 1/2 multiplied by the difference of the bonding electrons to non-bonding electrons. So in the case of the H2 molecule, 1/2, we have 2 bonding electrons, we have no anti-bonding electrons, so that gives a bond order of 1. So that's pretty simple to do, and you can see here that what increases bond order is having electrons in bonding orbitals, and what's going to decrease bond order is having electrons in anti-bonding orbitals. And the important thing is that as long as we have more electrons in bonding than we do in anti, we will get a positive bond order. So we can do the same thing for other elements that are in the S block of the periodic table, or even in the P block of the periodic table. But if we look at, say, helium, when 2 helium atoms come together, we know from experience it doesn't form a molecule. Molecular orbital theory can explain that. So helium, a helium atom has electron configuration 1s2. So again, we've got 2 isolated helium atoms. Now we think about what happens when these guys come together and their 1s orbitals overlap. Well, if those 1s orbitals overlap in phase, we will form a sigma 1s bonding molecular orbital, and if they overlap out of phase, we'll form a sigma star 1s anti-bonding orbital. So we've got 2 electrons from each of our 2 helium atoms, so that gives us 4 electrons total that we have to put into our molecular orbital diagram. The molecular orbital diagram is just that little bit in the middle there. And so we've got 1, 2, 3, 4. So if I calculate the bond order for this, remember it's bonding, 1/2 of bonding minus anti-bonding, we get a bond order of 0. And we know this, that helium does not exist as He2 molecules, it exists as individual helium atoms, because when 2 helium atoms come together and collide, they're not going to stick because they can't form a stable molecule with a bond order that's greater than 0. So there are some other things that we can do. Let's have a look at lithium. Lithium has valence electron configuration 2s1, and when we construct the molecular orbital diagram from lithium by overlapping the 2s orbitals on 2 lithium atoms, we end up with an MO diagram that looks like this. We've got a sigma 2s here and a sigma 2s star. We need to put 2 electrons in here, one from each lithium atom, and we get 1, 2. So we would expect that lithium 2, all of its electrons are paired up. It would be what we refer to as diamagnetic, and the bond order 1/2 of 2 minus 0 gives me 1. So we would expect that lithium 2 exists. Now, if I go to beryllium, beryllium is in group 2A, right next to lithium, and it has valence electron configuration 2s2. So if 2 of these guys come together, I'm going to end up again, their 2s orbitals will be overlapping, forming a sigma 2s and a sigma star 2s. But now I've got to put in 4 electrons. So 1, 2, 3, 4. So when I calculate the bond order now, 1/2 times 4 of that 2 minus 2, 2 bonding, 2 anti-bonding, end up with a bond order of 0. So this guy we wouldn't expect to exist, and that's exactly what we find. There you go. So it's non-existent. So we can't talk about whether something is paramagnetic or diamagnetic if it's non-existent. And it turns out that this is exactly what we see experimentally. And of course, we already knew dilithium existed because of Star Trek, where it's used in the warp drive. Okay. Now, once we move beyond, H2, He2, lithium 2, and Be2, we're then firmly into the P block. So hydrogen is 1s1, helium is 1s2. These are the valence electron shell configurations. Lithium is 2s1, beryllium is 2s2. When we get to boron, we have valence shell electron configuration 2s2 to P1. So it starts getting a little bit more complicated because now we have to start considering how do p orbitals overlap. So when 2 p orbitals that are along the bond axis combine, they're going to overlap in a sigma fashion. And so when these guys overlap, here's the center of one atom, here's the center of another atom, these guys just come together and they're going to overlap and they're going to form, if they come together in phase, a sigma 2p molecular orbital, and if they come together out of phase, a sigma star 2p molecular orbital. So there's only going to be, one possibility for these guys coming in together with this particular orientation, but we know that a p subshell is comprised of 3 p orbitals. We've explained how one set of those orbitals can overlap. What about these guys here? So the remaining pair of p orbitals, they lie at 90 degrees to the bond axis. And so when they come together and overlap, they're going to overlap side on and they're going to form pi and pi star MOs. So there's another 2 that are going to be able to do this. So these 2 on each of our atoms are going to come together and form 2 lots of pi bonding molecular orbitals and 2 lots of pi anti-bonding molecular orbitals where they come together out of phase. So when the p subshells on 2 different atoms overlap, you end up forming a set of sigma bonding orbitals, a set of pi bonding orbitals, a set of sigma anti-bonding orbitals, and a set of pi anti-bonding orbitals. So it gets very complicated as we move into the p block. So here's nitrogen, and if you remember, we said before that nitrogen was diamagnetic, and so that means it has no unpaired electrons. Now, every nitrogen atom has 5 valence electrons. So when we form N2, we're going to have to place 10 valence electrons in the MO diagram. So looking at the valence electrons on each nitrogen atom, nitrogen has valence electron shell configuration 2s2, 2p3. So here's a single nitrogen atom, 2s2. Here's the other single nitrogen atom, 2s2. When these guys come together, we're just going to form a sigma 2s if they come together in phase, and a sigma star 2s if they come together out of phase. And we have to put 1, 2, 3, 4 electrons into those orbitals. So dealing with that part was pretty easy. What about when the 2p subshells on 2 different nitrogen atoms overlap? Well, one pair will overlap to form a sigma 2p and a sigma star 2p, and then the remaining 2 pairs, they're going to overlap to form 2 pi 2p's bonding orbitals and 2 pi star 2p anti-bonding orbitals. And the anti-bonding, the pi orbitals are 90 degrees to each other and also 90 degrees to the sigma molecular orbitals. So from the bottom to the top, we have to put in 10 valence electrons. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see everything's paired up. Nitrogen is diamagnetic, doesn't stick to a magnet. Molecular orbital theory is doing a great job. What would be the bond order here? 1/2 times bonding electrons. So we've got 2, 4, 6, 8 minus anti-bonding electrons, 1, 2. 1/2 times 6. It's going to be third order. And what do we know? There's a triple bond in nitrogen. So everything seems to be working, and we're also able to explain the magnetic properties. So for the first 3 members of the P block, their molecular orbitals all follow this pattern. There's 2 of the pi, okay? So they all go sigma, sigma star, pi 2p, sigma 2p, pi star 2p, sigma star 2p for B2, C2, and N2 for the diatomic molecules formed by the first 3 members of the P block of period 2. They all have this pattern, and we should be able to put enough electrons in there. So boron has 3 valence electrons because it's in group 3A. There's 2 of these atoms coming together. We need to put 6 electrons into its MO diagram. 1, 2, 3, 4, 5, 6. When you work through, you can see that this is paramagnetic because we've got 2 unpaired electrons. And then if we do the bond order, it's 1/2 of bonding minus anti-bonding. So 1/2 of, we've got 2 bonding, and then another 2 bonding, we've got 4 bonding, minus 2 anti-bonding, so that gives me 2 anti-bonding, times the 2 times by 1/2, and gives me a bond order of 1. Carbon is in group 4A, so a single carbon would have 4 valence electrons. There's 2 of them, so we have to put 8 valence electrons into the orbital diagram. So it goes 1, 2, 3, 4, 5, 6, 7, 8. It's going to be diamagnetic because we have no unpaired electrons. And if we work through the bond order, 1/2 of bonding, so we've got 2, 4, 6, minus anti-bonding 2. So that's going to be a double bond, okay, bond order of 2. Alright, so N2, nitrogen's in group 5. We've got 2 nitrogen atoms, so we have 10 valence electrons we have to put into the MO diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are no unpaired electrons, so it's diamagnetic. If I work on the bond order here, we've got 2, 4, 6, 8 bonding. minus 1, 2 anti-bonding. So 8 minus 2 gives me 6 times a half. That's going to be a triple bond in that molecule. So if we know the order of the molecular orbitals, we can draw an MO diagram for the molecule, or alternatively we could draw an electron configuration for the molecule if we wanted to, just like we can for an atom. Now, something weird happens as a result of a phenomenon called sp mixing, but when we move to the final members of the last 4 members of the P block, there's a flipping of 2 of our MOs. So in particular, those 2 flip. Okay, so everything else is the same as what we saw for the first 3 members of the P block, but the order of MOs flips in here. So we just have to kind of keep that in mind. But the same principle happens. So you can see that here, that the pi 2p and the sigma 2p, they flip in there. All right, and then that remains the same for the last 3 members of the P block. So again, just as long as you remember that, and how I remember it is that the first 3 members, which are B2, C2, and N2, they get pi first. So I just remember that the first 3 get pi. They get the pi, or get the pi first. Okay, and then they flip for the other ones, but everything else stays the same. So O2, 6 valence electrons to put in there. There's 2 oxygen atoms, so you have to put in 12 electrons. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's going to be paramagnetic. And if I work out the bond order, you see that it's second order. There's a double bond in the oxygen molecule. When it comes to fluorine, fluorine's in group 7. I've got 2 fluorine atoms in my molecule, so I have to place 14 electrons in the MO diagram. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's no unpaired electrons, it's diamagnetic, and if you work through the math, you'll see that it has a bond order of first order. Now, when we get to neon, neon's in group 8, we've got 2 atoms in our molecule, so we have to put in 16 electrons. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And when I work on the bond order, you'll see that there are 8 electrons that are in bonding molecular orbitals. So 2, 4, 6, 8. And then there are also 8 electrons that are in antibonding orbitals. So 2, 4, 6, 8. So we end up with 1/2 of 8 minus 8. Well, that equals 0. And neon 2 doesn't exist, and we know that because neon exists as individual atoms, whereas these other things, they have a bond order greater than 0 and they exist as diatomic molecules. Okay, so this is kind of a tricky section, but you really just have to recognize that you have 3 different types of MOs and 3 different types of molecular orbital diagrams. The first for the S block, and then you have one for the first 3 of the P block, and then you have another type of MO for the second 3 of the P block. So you have 3 different types of MO diagrams to really commit to memory. And then you just have to put the correct number of electrons in there and comment on whether your molecule is paramagnetic or diamagnetic, or whether it's stable or unstable, and what the bond order is. So I would like you to have an attempt at these 4 questions, and I'll be working through those on Wednesday in the Zoom session.